All right. Hear ye, hear ye. Here's the top of the hour. This is 2 p.m. And it is my pleasure to introduce to you the Leon, who's going to talk about the packets made him do it. Leon Ward, everyone.
Let's try that again. There we go. Yes, so thank you very much for choosing to join me for this Wall of Sheep DEF CON workshop on the packets made me do it. Not to be confused with the pockets mode me do it, which is clearly what this font makes it look like. But trust me, I'll be talking about packets and not pockets today. So I'd like to start off, if I may, by letting you in on a little secret. And it's a bit of an embarrassing secret to say here at the Wall of Sheep. And that is, I hate looking at packets. I really do. There was a time when I was quite kind of passionate about it. I found it very interesting, doing a lot of packet analysis. You learn a lot of things, but those times have long gone. But there's one thing right now that I hate more than looking at packets. And that's not being able to look at the packets when I really need to or want to. And that situation is the thing that led me to invest a big chunk of time and effort over the last couple of years putting together this framework for distributed packet capture that's designed to integrate with your pre-existing network security tools to retrofit them and retrofit your analysis workflow or your analysts' analysis workflow with packet data when they need it. So in this 45-minute or so session, we're going to look at the following. Introductions. Sorry, I should have introduced myself, really. I've been working in network security and information security for about 15 years now, almost exclusively from a defensive posture rather than an attacking posture. I've put together and helped work on very large network security deployments, intrusion prevention technologies that span across the globe, and intrusion detection. And spent a lot of time working with this little guy, the snort technology as well. So today we're going to talk about FPC, full packet capture. So we'll start off with some basics and review what a packet is, because this is where we're at. And then we'll look at some of the challenges you get into with trying to deploy a large-scale network security monitoring, or rather, network security recording technology such as full packet capture. Then we'll spend some time looking at the actual tool itself, how it's put together, how the components link with each other, some of the decisions that I've made along the way about how things can work together best by learning some painful problems where I've wasted some time on some bad decisions. Then we're going to have a little live demo and let you see the technology in action, and we'll look at very specifically a Wall of Sheep style use case, where an external security monitoring tool has detected a session that's interesting. And because in this case, it could be exposing user identity data, and you want to see the actual content of that TCP flow. But you don't have that flow in the tool that's detected it. So you're going to pivot over to OpenFPC and jump straight to that flow that's interesting. I also want to start off with a quick teaser, because I realize many of you in the audience would have had a lot of experience working with full packet capture tools as well, so you don't want to sit through some of the basics. You want to get an idea of what this tool set can give you very quickly. So I'm going to show you a quick video rather than a live demo, just roughly where we're going to end up in the next 40 minutes or so. That is, if VLC is going to be kind to me. Okay, so this is a screen recording of me using a network security tool. This isn't the user interface for OpenFPC. This is another very well-known security technology, but it's going to provide me a good example of enriching the detection that doesn't have packets with packets from OpenFPC. So into this system, I've imported some of my own custom intelligence, and it's just an IP resolution intelligence. So there's a list of IP addresses that are associated with this group called the super evil APT groups. And the technology is doing exactly what I've asked it to do. It's looking for communications to these IP addresses, and it's raising, if you can see them, IP monitor events when it's seeing communication to them. It doesn't supply me with the packets, it's just supplying me with the IP address. But I'm specifically interested in what's been communicating between this 42.74 address and this destination IP address. So the first thing I'm going to do from my web browser is I will right-click and go and talk to OpenFPC through a browser plugin. And that's immediately told me that the system's ready to go, and I can communicate it through with it through the browser. So it's saying I've got 7 days and 28 minutes or so of storage to look back over. But now I want to go grab those sessions. So instead of pulling up another web browser window and talking to another user interface, I simply highlight the stuff that I'm interested in, right-click, and go to different sides of actions I can put to OpenFPC. And the bottom one there was work it out. I've just given it a string of data. It's going to look for IP addresses and things that could identify sessions in there, like port numbers. And it's going to go and grab those that data for me and bring it straight back to my browser. And back to my client machine. And there you can see the ICMP traffic followed up by a couple of TCP sessions. And just to prove that it does have the full packets, just to right-click on that, I can see the communication with that super evil APT group is clearly some super awesome command and control communications. So that's one use case. That's where I've got a specific thing that I'm interested in. Second thing is I've got 2 bits of disparate data that aren't in a single event. So here I want to see other communications that may have existed around this timestamp from a different IP address. So I build a query by selecting things, adding to the system, and once I've built a query based on any data that's in the browser, I can pop up the browser window, hit search, and there you go. That's all the communications that took place between those 2 nodes at a set amount of time. You can, of course, make some customizations there of whatever you want to search for. So I'm going to look for data to port 53, the last 200 sessions that have been communicated with it, and if I want to actually see the packets of those, click fetch, and they'll come straight down to our browser. So what's the takeaway from that? This approach has enriched the analyst's ability to look at data without leaving the web browser, without leaving the tools he's already looking at. He's got the context of what he's interested in the background and the packets in the foreground. And I found that's a pretty powerful way of doing integration with technologies that don't support packet capture. So let's go from the advanced stuff right back to the basics. If you're going to capture packets, what is one? What is a full packet? So here's a quick little view of a packet that's been captured by a TCP dump. We can see it says sudo TCP dump minus NI, so specifying an interface to capture on, minus S0, that's the snap length, so I want to have the whole packet rather than truncate it to the first few bytes. Minus double capital X, that means dump the link layer data as well to the output, including some hexadecimal, or rather some hex rendering of that data, so it's more human readable, or ASCII representation of that hex, and just one packet. And the constraint is UDP port 53, so we're just looking at the first packet that matches that constraint. So that's kind of a packet, but in reality, that's the only stuff that's there that is the full packet. All of the text in black is some helpful output from TCP dump to tell us it's doing its job with some verbosity. The red stuff, if you can make out the colors, which are kind of impossible for me to make out because this light has just completely blinded me. But the red stuff, if you can make out the color, is what TCP dump has decoded for me to make the analysis process easy to understand. So we don't have to manually decode each and every byte. We can see what it says. So there you go. That's as easy as pie. That's a full packet being captured. So why is it hard? Why is it hard to do on a large distributed scale? Well, there's a couple of reasons. Excuse me. Yeah, there's a couple of reasons. So scale, in terms of volume and data rate, is a challenge. A lot of packets means a lot of storage and a lot of I/O on network interfaces, and we'll look at that in a second. The other thing is the distributed nature of networks. It's hard to actually capture all the data you want to capture in a way that's easy to access for the person designing the deployment. One example of where that's really hard is where you try to capture data towards the core of the network. Not actually at the core, but towards the core. You run into challenges with asymmetric traffic where traffic flows in different directions, and we'll look at that in a second. And keeping around enough data to be able to perform a human analysis process on packets is really hard, because people work much slower than automated tools. But the benefits, if you get it right, you don't even have to get it totally perfectly correct in terms of a deployment. If you get it nearly right and you have the data you need on that day you needed it, the benefits are amazing. And it's really helpful for anyone who's skeptical about the data security tools present to them. And we'll look at some examples of that. So here's a couple of examples of why scale is hard. This is some very simple back of a fag packet, some maths I put together. It's not super accurate, but it gives you an impression of the amount of storage you need to work with different types of network speeds. It assumes like every link is 100% utilized all day, but it gives you a feeling of the area of the scope of the challenge you've got with storage. Something like a 10 megabits per second perimeter link requires up to 106 gig of storage a day. That's not hard. You can do that on laptops. That's easy to hit. 100 megabit pipes giving you 1 terabyte a day. That's walk in the park stuff for modern computing. But 40 gigs of traffic a day, you need to throw a lot of money and a lot of investment at deploying classic types of this technology at high speeds. And there are commonly other options. Ultimately, this is an economics battle. You can't capture all the traffic all the time. So there's some strategies you can use to focus on where you actually want to invest your time capturing. Second thing, distributed networks and getting access to the data on the network. Ultimately, you've got to be close to it. That might sound silly, but there are times around to situations where people haven't really thought that through. If you've got a web app that's, say, co-hosted one element in London, another element in New York, you want to do full packet capture on that web app, you've got to have a box in both places. It doesn't make sense to try and push all the packets to one central location. Put the capturing technologies where the assets are that you want to actually monitor. I mentioned asymmetric traffic earlier. This is everywhere. Asymmetric traffic appears inside networks when you move further away from the specific assets or devices you want to monitor. If you think about my laptop here, every packet I put out on a Cat5 cable, it goes out and comes back in on the same cable. There's no asymmetry there. You run into this situation of asymmetry where a packet takes a different route out to the return path when you get into deployments and networks where there's a lot of high availability active-active HA technology is deployed. You probably will see network maps where you've got like twin switches, twin routers, twin switches, twin routers, and things all the way up. The routing decisions, by the way, this is really hard for me to say route, but rather than route, but I'm trying to do it just so you can understand me. The routing decisions everything makes on the way up could be different on the way down. Now that leaves you in a bit of a situation with full packet capture, because if you're just on one of those links, you only see you only hear half of a conversation. And that's really hard to work with, or rather it's impossible to really work with to do a really good analysis process when you only see half of a conversation. It's a bit like when you get a telephone call and you're in a crowded room and you don't want everyone in the room to know who you're talking to. You say, oh, hi mum, sorry, I'm busy, and you wave everyone out and walk off and make a phone call, and it's somebody else. It's a recruiter or somebody else. That's exactly the same situation when you only have one half of the data. You only see one half of the conversation. It's impossible to do any real analysis of what's taking place, especially with some modern command and control protocols. You've got to get over this situation. You need to architect your deployments in a way where you can monitor both points and merge, reassemble all that traffic to do the analysis. It's impossible to ask the networking teams to re-architect their networks to get rid of asymmetry. It just won't happen. So that's one of the things that I want to design into OpenFPC, is to deal with this situation, where you can recombine streams from either over interfaces or over geographically dispersed links where you need two separate devices, where you can bring that data back into one single stream and work on it like it was the original endpoint that you're trying to monitor. So good habits for security analysts. I mentioned the benefits of doing full packet capture are really good, even though it's pretty hard to deploy. This is an example of that. I find really good security engineers, malware engineers, reversers, instant handlers have got something in common. And that thing they've got in common is skepticism. They're natural skeptics. In a situation like this where we have a tool, which is Splunk I'm using as an example, so credit to the guys over there, Splunk is telling an analyst here something about an event. And if we look at it, we can see that event is some Tor exit node, some outbound communications. I realize now that outbound is spelt wrong as well, which is a good fail. Some outbound communications to an IP address. So from a security analyst perspective, what does this mean? Well, we don't actually have enough context. As a skeptic, you might say, I don't believe this is happening. Is this really communications with a Tor exit node? Where did you get that assertion from? What makes this tool tell me that it's communicating with Tor? So you want some more data. So without that more data, you can't really understand if this is real or not. So understanding where this data source came from, which is from an intelligence feed. This is a real-world example, by the way, that I ran into a couple of weeks ago. So this isn't something contrived, it's real world. If you try and work out where the intelligence feed came from, in this example, it came from the Tor project. They openly publish all their exit nodes. So that's a great intelligence feed. But was it really Tor that it was talking to that device? Do we need to go and find who the user is inside our organization that's leveraging Tor to try and stay anonymous from our own security monitoring technologies? Or is something else that's quite benign going on? Well, in this very specific example, we could find out after doing some research with OpenFPC that device that's providing the very valuable service of Tor for the outside world is also providing this super valuable service of NTP, and the same IP address is providing both services. So without the ability to drill into the context of understanding why that detection happened and what data is that assertion of something like Tor communications based on, you can't really be sure. And that skepticism is really important with doing the analysis. So it's really important to get that data. So why don't all security tools provide it? Well, ultimately, it's really hard. You saw some of these scale challenges that I mentioned earlier, and it's expensive to put that amount of storage into network security tools. But in addition to the costs in terms of like the actual added cost of the box that the vendor needs to sell you and therefore make an equivalent margin that makes it more expensive, the effort of actually presenting that data to a user is super hard. I've actually been in situations where I've got user feedback and marketing feedback when I've worked on sort of designing products, that presenting packet data to a user can be a really bad thing because it makes a user interface look more complicated. It makes it look like you've got to be an expert to understand it. And nobody really designs mass market security tools just for experts because you limit your addressable market. So it has to be simplified to be as easy as possible. And that impacts the ability to have that data available. Another challenge is the computational and resource overhead of storing that data. It's not just disk space. If you need to if you reassemble streams and keep streams around in memory for longer, you need to have more CPU and more memory available to be able to perform that. That can take the processing and the resources away from whatever the tool is doing that you bought it for. For example, if it's a web application firewall, do you want it to be wasting its memory by storing and streaming PCAPs when it could be actually providing web application firewall services? There's also a challenge with political and legal issues as well. Monitoring is a challenge to implement depending on where you are in the world and what type of network you're trying to deploy monitoring onto. If anyone in this room is from Germany or France, you'll be very familiar with some of the challenges of deploying any of this stuff over there. So if you're a large organization that's trying to distribute monitoring across the globe, you've got to be aware of all of these legal challenges. And if you're putting that technology into your security tools, it can create some challenges with deploying that box, that security tool, to certain countries if it has this capability of recording packets in there. So that's the introduction. Now let's start talking about the tool itself, OpenFPC, and how you can get it up and running on your own common off-the-shelf hardware very easily, very quickly. Before I just focus all my time talking about that one tool, I want to call out that there are many other options available. This OpenFPC may not be the best thing to solve your problem. You've got other options. A lot of these technologies have come around over the last few years that are leveraging Hadoop and big data analysis technologies to stick packets into large data systems or big data systems, do some indexing, provide some user interface, some searching capabilities. OpenFPC doesn't take that approach. It doesn't require things like clusters. So make sure you go and have a look at some of the other options that are available out there. Some of them are new, some of them come from well-known security vendors that are open source projects like the Google Stenographer and OpenSock that's put together by Cisco. PacketPig, which was open source, I believe was picked up by another security vendor recently. And Squeal, that's been around forever as a network security monitoring framework. This integrates with Snort and things. So there are other options. This might not be the best one for you. So why could it be the best option for you in certain situations? When I designed it, I wanted to focus on very specific things and try and solve those specific goals and ignore other things. So the things I wanted to avoid was vertical scaling. To try and deal with more data and different types of networks, I didn't want to say you've got to put more computational resource into the box. It's designed to scale horizontally through a distributed architecture rather than vertically. I also didn't want to focus on threat detection. Remember, OpenFPC was designed to integrate with existing tools you have, such as next-gen firewalls, web application firewalls, advanced malware protection technologies, IDSs, whatever it may be. So I wanted to remove any form of threat detection from it itself. The assumption is you want packets because another tool has told you you should go and have a look at those packets. Getting access to the data is one of the things that current tools just didn't provide. You could record packets, but you couldn't get the data out of those data stores. So I needed to look at that. Leveraging automation, and I'm talking about that in depth in a few more slides, but that's really important. To be able to hook into other automation systems, to be able to get data out of the system automatically so you can have the packets available in the future when you may need them. So what are the tools and what are the dependencies? So the ingredients that go into the system, some are external, some are internal. The external tools, it leverages a couple of well-known and very good technologies. Daemon Logger, that's written by Marty Resch, the guy who wrote Snort. And CS Tracker is a flow tracker. It doesn't record full packets, it actually records session metadata. So what you saw in the demo earlier about searching for sessions, that data came out of CS Tracker. CX2DB is an interface that also looks at those flows and puts them into a database for indexing. I had to fork that as part of OpenFPC to allow it to work with the framework. It uses a MySQL backend, which you may think, hey, that's crazy. But the way you use flow within this system is that it only needs to record the flows for what you have packet storage for. So really, the bottleneck here is your packet storage rather than the flow storage. It's written in Perl. I know that's an unfashionable language at the moment, but hey, it's kind of a hipster language if you think of it in some ways. And it leverages the Dancer framework, which is a super cool Perl framework for developing rapid web services. It's got a RESTful interface, so you can just connect up to it, ask for some data, and it gets back. That's a super cool technology, Dancer. Take a look at it, or Dancer 2, in fact. Internally, it's a client-server architecture. So you've got a daemon that sits there. I'll talk about the daemon in the next slide. So you've got the Q daemon, and you've got a client which sits on your machine. The REST API, it just sits there asking for, waiting to have questions asked for it, and it will broker those questions or those methods to the Q daemon. So it's like an abstraction layer for simple integration. The whole system is configured by a single configuration file. So you don't have to spend hours trying to configure different type of components. If you need to change it in any way, you just update the config, restart it, and everything updates. So if you say like interface ETH1, and you want to change that to ETH2, change it, and everything will start working on that other interface. So the Q daemon, what does that do? It listens for network connections and allows you to ask it certain, or rather, exert certain actions. those actions are status, fetch, store, API key, and search. And there's another couple as well, but those are less relevant. Status is, how's the whole system doing? Is storage keeping up? Are you struggling with load? What's the oldest packet? What's the newest session? How's the session database working versus the packet storage? All data like that. So it's got this inbuilt sort of health monitoring technology in there. Fetch. Fetch is an action that's specific to that an analyst would want. I'm interested in packets like this. Give them to me and give them to me as quick as you can. I want to fetch them. Bring them back to my workstation. Store is for automation. We'll talk about that later. This is where it doesn't bring the packets back to the analyst. It says put them somewhere that I can access them later for later analysis. API key is about managing API key access to the REST APIs, so you can update, change, and get your API key out of this system itself. And search is simply look for sessions. And depending on how you execute it, you get that data back differently. From a command line tool, you get a semi-nicely formatted data set in your console. And if you use the REST API, you get a JSON blob back with all of the session data that you've asked for. The client software is installed on the client. It's also written in Perl. It works fine on Mac OS X, which is what I use in addition to Linux. And the platform I make everything on is Ubuntu long-term support, LTS. So it does work very well on Debian as well, but your mileage may vary with dependencies and other things. So the node is the thing that performs the capture. That's the thing you deploy multiple instances of around the network to have your distributed capability. It provides all the session capture, packet capture. It does all the logging. There's forensic logging in there, for example. So any session you ask from it, it will create a hash of the data it gives you back in case you need to use it for other steps in later legal follow-up to an event. And it does all the access control as well. So let's look at how it all hooks together. To the top end, you've got a sniffing interface, which here is ETH0, and at the back end, you've got a management interface. So you could have both on the same if you wanted, but in most deployments, you'll have the back end network on a separate management network. Traffic comes into the top, and then it's split up into two places. Daemon Logger stores the data. Inside OpenFPC, it leverages a controlled amount of data that you want to allocate to packet storage per box. So if you did go out and buy a large box for just running OpenFPC, you'll probably set up a logical volume and a partition as big as possible to capture as much data as you can. Natively, OpenFPC leverages a percentage. So it says use up to 90% of this partition for storing PCAPs, and it handles all the rollover. Most of all that logic actually came from Daemon Logger itself. So you got the packets, and they're sitting there somewhere. The other route that it takes is to put sessions into the session database. The goal of the session database is just to help you find packets you may be interested in a faster way, because it takes a little while to get access to the packets. You've got to perhaps go and carve out across the sessions across multiple large files. So the session database allows you to get a rapid idea of what data you're going to get before you go and ask for it. The interface to all of this is the QDaemon. So the QDaemon talks to both the session data and also the PCAP data and brokers the communications from your client to the system. And the reason it's a client-server system is that I didn't want to ever be in a situation where to get the packets, you would have to SSH into a server and then SCP data back. It's all part of the all part of the interface itself. You can have multiple nodes on one physical bit of hardware. So in situations where you want to have two network interfaces connected up to two different areas of the network and have logical separation from them and reference them in different ways, you can do that. So in this example, perhaps switch 1 is your email demilitarized zone and your connection into switch 2 is your database backend. You could connect it up to the QDaemon and say, give me packets from my demilitarized zone or my DB backend. So that kind of introduces the next concept, which is quite valuable here, which is the proxy capability. The QDaemon can actually run in two modes. One mode is the node mode, where it's doing all the session capture and the packet storage. The second mode is where it exists and you can ask it for certain questions, but it doesn't actually capture and store any packets. It leverages other nodes to be able to get that data. Excuse me. So in this example, I've got OpenFPC client installed on an analyst workstation in the middle, and the deployment spans to. So I'm hearing things. Okay, so another talk. So in this situation, we've got a global deployment of nodes in a distributed manner across 2 different continents. We've got a set in the US and a set in Europe, in London, Paris, and Amsterdam, and the US, New York, Vegas, and Baltimore. And if at any point I can ask for that data by connecting up to any node from my workstation. So I just say, I want to fetch traffic that matches this BPF from this node in JFK, and it'll go get that data for me. Now, if I wanted to perform a more distributed search, I don't want to ask that question 6 times across all boxes. So if I wanted to get all the data from the US, I ask for the US. If I don't specify a specific node, it'll execute this extraction across all nodes south of it. So JFK, Las Vegas, and BWI. The proxy would then actually reassemble all that data into a single stream and give that back to me as a single PCAP file from all of the US. And of course, you can stack these things. So if you want to get the data from the whole world, you ask from the one point, and it goes and splits up into ask both proxies, and they both go get all that data. So the analyst gets back a single PCAP that contains all the traffic that matches that BPF. So I mentioned these earlier. Fetch, go get the packets, I'm waiting for them. Search, look for sessions, and store. Add the data to an extract queue for later extraction. So that store is actually quite important with automation. So you can exert multiple actions on the queue daemon at one time. And that's what's being represented here as the green boxes. This one client has managed to request a status, a search or multiple searches, and multiple fetches to take place at one time. As soon as a request comes in, a process is forked, and it goes and gets that data for you. But with this store action, it doesn't provide back a PCAP or a chunk of data. It tells you about where you can get that data later on. So in this case, from a command line, it gives me back a remote file name I can go and extract when I'm interested. And over the REST API, it gives me a request ID and the position that currently has in the queue that I could go and pick up via another call to the REST API later on. So this is really important to try and make best use of storage resources you may have in your deployment. PCAP data is big, really big. And security event data is relatively small. It can grow to be big as well, but it's much smaller relative to the full packet data. So in a situation where you've got multiple security tools and they're recording events, in this example, maybe you've only got a full 1 gig of storage available for your security events. Maybe that allows you to have a few weeks worth of event data. But with a terabyte of PCAPs, you only get a window of 1 day to get access to the data you're interested in. So you go home at the weekend, and a security event happens on Saturday. You come in on Monday, and you look at that event, and you say, I really want to see the packets for that event, but they've gone. They've expired from your buffer, which is only 1 day long. The store action enables you to leverage automation with some pre-qualification on that data. So if you get an event that has a session identifier, and that turns up in your security event store, you can automatically go and talk to the queue daemon to go extract that session and go stick it somewhere else for later analysis. So that enables you to optimize storage of only storing the sessions you're explicitly interested in. Perhaps in an example of something like an intrusion detection system, only store the full session data of just the sessions that cause an eventifier. That does lower your analysis capability, but it gives you a really good trade-off over the weekend when you're not there to actually look at the data. It's important to mention time, so 2 more things before I show you some demos. Time is used as an anchor, and time is specified with 4 different arguments to OpenFPC. S time, E time, start time, and end time, so a window give me all packets that match this BPF between this window, which is probably the most logical way of requesting data, but also the longest to actually type in on a command line, because that takes a while. A timestamp. Timestamps are important because you get them out of detection events. So malware is detected at this time. You want packets from around that time in the session identifiers that were raised within your security event. So you can just specify a timestamp, and they get you data that occurs around that time. And last, which can be added, combined with timestamp as well, is just give me data from the last X minutes, or rather, it's specified in seconds actually. So the last 600 seconds will give you the last few minutes. The reason it's important is because of the way this data is stored. So it's all time-bound into buckets on the PCAP side. So every PCAP file that daemon logger creates, it has a timestamp associated with the first packet in it. Actually, it's not the first packet. It's the time that PCAP file was started. So you know there's no packets older than that timestamp, but the first PCAP could have taken a couple of seconds before it came in. First packet could have been a couple of seconds before it came in. So when we're specifying something like this example, where we know our oldest packet in our whole system is from 11 o'clock on the 30th of July, and we're interested in a session from 11 minutes past 11 and 11:21, we know what files we need to go and focus our extraction in. So it allows us to constrain what we look for. So if you have terabytes of data, you're not walking all those terabytes of data for sessions you're interested in unless you really have to. The other thing to mention is the way of specifying data. And you may have noticed this with the first example of the work kit out in the Chrome extension. You can ask for data in different ways. The most simplistic for anybody who's looking for a session is probably just type in this example at the top. SIP equals an IP address, destination IP address equals this, a port number and a proto. Easy to understand. If you're an analyst that's used to working with BPFs, you could just ask it for a BPF. But the interesting thing is, the tools that OpenFPC is designed to integrate with don't normally put out BPFs. They don't put out session identifiers. They put out log lines. So in this situation, I'm asking to fetch data that's relevant to a log line from a third-party tool. It decodes that log event itself and gives you the session that it's relevant to. I'm embarrassed to say I can't actually remember what log format this is in this slide, but there's two underneath that I do recognize. So the first one is a syslog event from Snort. So just Snort outputting data of a syslog. And in that event, we can see the stuff that's bold and highlighted. It can leverage to understand the session. So we've got a timestamp of when we're interested in the data. We've got a protocol, a source IP address, a source port, a destination IP address, and destination port. That's one specific session. You can't get more specific than that. Other event types are much more generic and open in their event logging. So the bottom one here is actually from XSIM. So here we've got an XSIM event saying there's something that's interesting coming into my mail server, but we've only got a timestamp and an IP address, and we know the protocol, which is ESMTP here. So we can still carve out the data that's relevant for that specific session, but we'll probably get more data than we expected as well. So this ability to actually pass tool output into the packet capture creates this interesting workflow that I didn't expect until I experienced it a few times. Something tells you there's interesting data on the left-hand side, raises you a log event. So you leverage OpenFPC to go grab that session. First thing you do is run it through some other tools to do some analysis on it. The output of those tools are more log lines. So you then leverage that new log line to go get more session. And you kind of keep going around in a circle until you get your analysis complete. And like I said, this is something I didn't expect when I was designing it. Let me give you an example. Something has caused me to become suspicious about DNS traffic coming from a certain IP address. So I leveraged the command line client to go fetch that data on the destination IP address and wrote it to a file name called alldns.pcap. I want to look at that data more closely, so I leverage a third-party tool to do that. Here I'm using passive DNS to read through all that DNS, all those DNS requests and responses, and put it into a format that I can look through easily. One of those events, or one of those log lines, was interesting. because it's resolving a host name which has caught my attention, evil.foo.com. What's evil about it? Could this be the thing that I'm interested in? So I then provide this log line back into OpenFPC, but it decodes it in a different way. It decodes it in a way that's contextual for that type of log type. Here we're not interested in the, if I can try and use my mouse to point, we're not interested in traffic from 1.1.1.1 to 8.8.8.8. That's the client talking to the DNS server. What we really want to know is, after that DNS resolution took place, what did this client talk to the target machine? So instead, we decode and take out the real target IP address, and we can gather following data that took place against the suspicious machine and actually the thing that did the resolution. So you can find out what they're talking about. Right, okay, so I'm kind of running tight on time, so I wanted to finish on two points. One, I wanted to say thanks to some people who wrote the tools. You know, you always stand on the shoulder of giants. Daemon Logger and CS Tracker are great tools. All I've really done is added a whole framework to interact with those tools. And the second thing is I wanted to put out a quick call for help. There's two things I'm struggling with. And if I can't ask a room like this, who can I ask? As you saw from that video at the start, the user interface for the Chrome extension is really ugly. I've got no styling in there. So anybody who knows about style sheets, make me something. It'd be really appreciated. And the second thing, if anyone's got some real first-hand experience of getting stuff into Ubuntu and Debian upstream for packaging, really interested in having a conversation afterwards. I've got Debs, but I'm looking for some best practice knowledge of actually how to automate the build process and get that upstream. So a couple of demos, and then I'll let you all go. Can you read this okay? So the first thing I want to do is ask the system for status. I haven't specified a server name or anything, but this is the client software is installed on my laptop here, and the server software is installed on a virtual machine I have. So it's still client server. I've got an RC file in my home directory that specifies like the common things I'm interested in, which is the server I want to connect to. So I can just ask it for things like status, and it will. And I've also saved my username in there as well, which I've just used for O for simplicity of typing in a demo. So I've asked the system for status, and in this example, I've connected up to a machine called Luxor. That's a proxy node, that's a proxy device and not a node. And south of that proxy, there are multiple machines connected into it, and they're in an up state, so that it's talking to them successfully. Those devices are Paris and Rio. And I can see the details of how both those devices are functioning. So the amount of status that's on them, the amount of package storage utilization, et cetera, et cetera. So that's the simple status. Now let's go and search for something. Search minus destination port 53. Last chunk of time. And if the demo gods are good, okay, and they're not good, let's go another longer. There we go. Let's see if this is easier to read. That probably makes it harder to read, but easier for the formatted eye. So this is a search that's taken place to Luxor, which is a proxy device that's asking for data that's been captured in both Paris and Rio. And when that data comes back to Luxor, my proxy, it's actually recombining it and putting it to time order. And you can see from my flow table here, you can see there's a node name that's actually returned. So it's from Paris, Rio, Paris, Paris, Rio. So it's recombined into one single coordinated set of data from multiple devices. And of course, here is only two being used, but it could be way more than two you could be talking to. Now, say I actually want to get those packets now. So I'm going to change my action from search to fetch. And this will take longer than the search, but it's going to give me back, there we go, a PCAP of all that data. Let's highlight the right thing. Let's open that up. There's all that data straight back to my my workstation. So the other demo I wanted to show was, I said, a wall of sheep use case. So in this situation, I've got a tool that is giving me event data. Let me zoom in a bit more. So this is I'm leveraging a tool here to look for assets on the network that could be exposing credentials that are interesting. And the first one you'll see in that list is something that uses plain text communications and could be linking some credentials. And I can see on the wall of sheep wall over there, there are many people who are giving up their credentials over IRC. But the tool that I'm using here doesn't give me the session. It just tells me, it doesn't give me the PCAP data. It just tells me this is an interesting session. So based on that data there, at the top there, this says there's a server listing on a certain port discovered at a certain time. I want to go get that full packet capture data. So I'm going to go use my client with an action of fetch. But instead of giving it a session identifier, I'm going to give it a log line. Oh, okay. So here we can see that it's returned back a PCAP file. I shark that file. There's the exact session that I would be interested in, and simply just going like this gives me all the PCAPs. It gives me enough data to understand what the username is of owned accounts, and somewhere down here we'll see it authenticates an XServe. There we go. I've run out of time, so I won't show you how easy it is to install, but trust me, it takes one command. And I would love to have any follow-up questions with anyone just around here afterwards. So thank you very much for listening.